Jnanam Paramam Dheyam. Knowledge is supreme.
In the last lectures, we have been studying field extensions, algebraic field extensions, and sometimes in between also I have used the words like algebraically close or algebraic closure of a field, etc. etc. Now we will prove the existence of algebraic closure for an arbitrary field, and also we will prove long pending statement which I have been saying, that is the fundamental theorem of algebra, which says that the field of complex numbers is algebraically closed. Alright, so first let me prove the existence of the algebraic closure. So this today's lecture is about the algebraic closure. Alright, so recall that a field E is called algebraically closed if every polynomial f with coefficients in E has a 0 in E. Then we call the field to be algebraically closed, and we will prove that C, this is what we will prove, this is the fundamental theorem of algebra. It says the field C of complex numbers is algebraically closed. This was this is also known as theorem of D'Alembert Gauss. D'Alembert stated this in 1746. D'Alembert was a French mathematician and Gauss was German, as one knows. This was proved in 1800, approximately 1801. That is Gauss, and Gauss's proof was the considered first complete correct proof of this theorem, which he did in approximately 1800. But there are other proofs also today, and the proof I am going to give will be based on the ideas of Lagrange, which was before Gauss. Okay, so let us prove. I want to prove that every field has an algebraic closure. But before that, let us observe some easy facts. So let E be a field. So E is algebraically closed. Algebraically closed. That means every polynomial with coefficients in E has a 0 in E. This is equivalent to saying every irreducible polynomial in Ex has a 0 in E. Because we know every polynomial is a product of irreducible polynomials. So if an irreducible factor has a 0, then the product will have also 0, the same 0. So I am noting these facts because I will use this without reference further. So this is also equivalent to E has no algebraic extension algebraic field extension of degree strictly bigger than 1. No algebraic extension of E has degree more than 1. So, that means the only algebraic extension of E is E itself. Also equivalent to saying that every irreducible polynomial in Ex is linear. Linear polynomials are the only irreducible polynomials. Okay. Also equivalent to saying that every polynomial in Ex splits into linear factors in Ex. This is also because every polynomial splits into irreducible ones, and irreducible polynomials are linear. Therefore, all these equivalences are just merely a restatement of the definition. So, I will use them whenever there is a possibility, and I will not explicitly say why it is so. So, now another easy proposition. So, let E over K be a field extension with E algebraically close then, and let us denote E ALG. This is by definition all those elements in E, Y in E, such that Y is algebraic over K. So, this is what we call it, the algebraic closure of K in E. We have seen that the algebraic closure is a subfield, and now this says if E was algebraically closed, then the assertion says that E algebraic, this ALG is algebraically closed, field, and obviously E ALG over K is an algebraic extension. This is clear because these are precisely all algebraic elements over K. So, this algebraic extension is clear. I want to show that E is algebraically closed field, and this is because E is algebraically closed. Okay, so let us prove this. So, proof, what do we want to show? We want to show that every polynomial, so we want to show that, so to show that if f is a polynomial with coefficients in this EALG, this is an irreducible polynomial, then I want to show that has then f has a 0 in EALG. This is what I want to show. Well, but f is a polynomial in EALG, coefficients are in EALG, that means the coefficients of f are algebraic elements over K. This is clearly, because this is a subfield of E, is clearly contained in this Ex. So, f is a polynomial in Ex, E is algebraically closed. F may or may not be irreducible in Ex because we are taking over a bigger field, but in any case this polynomial will have a 0 in E because E is algebraically closed. Then f has a 0 in E since E is algebraically closed, and let us call that 0, f has a 0. So f of y is 0 for some y in E. I want to actually check that this y lies in EALG. So to show that, we will show that y is in EALG. That means I want to show that y is actually algebraic over E, algebraic over K. So this is to show. Well, but what do we know? We know the following thing: K is here, EALG is here, E is here, and in this I want to adjoin that y which is here. Now this y is an element in E. Y was an element here, and y satisfies the polynomial f. So note that this extension is algebraic by definition of this, and this extension is also algebraic because this y satisfies the polynomial fy. This f was polynomial in E, has coefficients in this. So therefore this extension is algebraic, this extension is algebraic, therefore composite is algebraic, the transitivity of algebraic elements. So this extension is algebraic. In particular, y is algebraic over K. In particular, y is algebraic over K. But this means, so that is y belong to EALG by definition of EALG. But then if y belong to EALG and this fy, so that means there is, so this means this x f which was an irreducible polynomial in EALG. This was irreducible in EALG. So this has to be a multiple of a minimal polynomial of y over K. Some constant a belonging to some constant, a belonging to where it doesn't matter. So therefore this f has a 0. So in particular f has a 0 y which is also in EALG. So that means we have proved that every irreducible polynomial in EALG x has a 0 in EALG. So that therefore, so this shows that, so therefore EALG is algebraically closed. This is what it proved. So remember, what we have proved is, if you have an algebraic extension, algebraically closed field which is an extension of a field, then the algebraic closure of this field in that is also algebraically closed. A typical situation is the following. So example, so we have Q here, and Q is a subfield of complex numbers, and fundamental theorem of algebra FTA says that this is algebraically closed. We have not yet proved, but we will prove this is algebraically closed. And now we take the algebraic closure of Q in C, that is also denoted by QALG. This is also standard notation is Q bar, which is by definition all those complex numbers Z in C such that Z is algebraic over Q. This is a field, it is called field of algebraic numbers. field of algebraic numbers. And the above proposition says that this is Q bar is algebraically closed by proposition. So because C is algebraically closed. Alright. So let us continue. So now I want to prove that every field has an algebraic closure. So first let us define properly what is an algebraic closure. So definition. Let K be a field a field extension, an algebraic closure of K is a field extension E over K such that two conditions. One is E over K is algebraic, that means every element of E is algebraic over K, and second, E is algebraically closed. So this means in some sense this is the smallest algebraically closed field which contains K. But this is more precise. The smallest means what? That is little bit loose, but this is proper. Now we want to show that given any field K, there is a field extension such that E is algebraic and E is algebraic over K and E is algebraically closed. So these theorems were proved by, so these are called Steinheit's theorems. Steinheit's theorems. And he proved these theorems in approximately in 1910, where the rigorous algebra started, or rigorous theory of fields was first done properly by Steinheit's in 1910. Steinheit's was a student of Kronecker, and also one of his teachers was Frobenius. So we will prove these precise theorems, and this was the first time was used. The main ingredient in the proof was a little bit abstract. That is why these theorems were proved only after the set theory became more prominent and transfinite methods of set theory was introduced by Cantor, and Steinheit's used them. Steinheit's used them in the proofs, and also worth noting that Steinheit's used axiom of choice, because but I am going to use Zorn's lemma. So the same proof, but instead of axiom of choice I am going to use Zorn's lemma, which is more comfortable. Zorn's lemma was proved in 1940s. Zorn was a student of Artin. Alright, so let us state the theorem. So this is the theorem we are going to prove. This is Steinheit's 1910. So every field K has an algebraic closure. Proof. As I said, the same proof, but this is arrangement from Emil Artin. And what we will use is, we will use so-called Zorn's lemma. Zorn's lemma will be used in this proof. So we know Zorn's lemma, which is equivalent to axiom of choice. Anyway, I am not going to go to these proofs. This is just for the side comments. And how will it be used? It will be used in the form that let me recall you that we are going to use this fact. This is known as Krull's theorem, which says that let A be a commutative ring and remember that our ring has always identity, but I will stress it here with identity, and A be an ideal in the ring A, then there exists a maximal ideal M in A, which contains with A is contained in M. So I will use this Krull's theorem, which uses Zorn's lemma, and therefore I said in the proof of this theorem we will use Zorn's lemma. And remember, in this Krull's theorem, commutativity is very important, and the ring with identity is also very important. All right. So let us continue the proof. We want to construct an algebraic closure for a given field. All right. So what do we do? First I will construct a ring. So what do we want to prove? So I want to do that for every irreducible polynomial. For every irreducible polynomial f in Kx, I want to we associate an indeterminate which I will denote by xf over k. So that means what? So, and the set of all irreducible polynomials I am going to denote by I R of Kx. This is the set of all irreducible polynomials in Kx. So there are many, infinitely many. In fact, if your field is uncountable, this also will be uncountably many, and so on. And I am going to consider a ring R, which is the polynomial ring over K in all these indeterminates xf, where f is varying in this set of irreducible polynomials in Kx. So this is a polynomial ring in infinitely many variables. This is a polynomial ring in so many variables. There are many variables. So we are going to consider this ring, and also I will consider ideal A in this ring R, which is generated by these elements. So this is the ideal generated by F, and you write instead of X, XF, F xf, where f is varying in irreducible polynomials of Kx. So this is an ideal generated by these polynomials. So that means all R linear combinations of these are contained there. Right? This is the ideal generated by this set is precisely all R linear combinations of these polynomials, f evaluated at xf. And the first thing is, now we claim that this is a proper ideal, because I want to choose a maximal ideal in this ring. So I will a maximal ideal which contains all these polynomials. So, I want to claim that this ideal A is, so we claim that this ideal A is a proper ideal. So, suppose the contrary, suppose not, that means what? A is R, but that means that is 1 will belong to A, but that means that is I will have an 1 can be written as a combination of R linear combination of finitely many polynomials. So, those are Fi, X Fi, I is from 1 to R, where GIs are arbitrary polynomials in R, and these are the generators of that ideal A. And I am looking for a contradiction. These Fi's were some irreducible polynomials. Now I am looking for a contradiction. So the contradiction will come because now I am going to use Kronecker theorem. Kronecker theorem says that if I have a polynomial over arbitrary field, then that polynomial splits. If I enlarge the field, then that polynomial will split completely into that field, enlarged field. So, Kronecker theorem I am going to apply to the polynomial f, which is the product of these finitely many Fi's. So, f1 to fr, this is a polynomial in Kx, and I will assume for each Fi, I is from 1 to R, there is a field L, finite extension, finite field extension L over K, such that f of ai, Fi of some ai is 0 with ai in L, and this is true for all I 1 to R. This is by Kronecker's theorem. Now, once I have that, we have this equation. This equation, I am going to substitute in that equation. So, substitute xi equal to this ai, this is for I equal to 1 to R, and all other variables, all other xh, put them to 0 for all other h in IRR kx. So, what do I get? I get 1 here. So, we will get 1 equal to summation I equal to 0, I equal to 1 to R, GI evaluated at this A1 to AR, and the remaining variables we are putting zeros, and Fi, all these variables we are putting AIs. But this, that is 0. Therefore, altogether 1 will be equal to 0, which is a contradiction, because which is a contradiction. So, therefore, this proves that the ideal A is cannot be unit ideal. So, it is a proper ideal, and hence there exists a maximal ideal M in R with A contained in M. And why maximal? Because we want to construct a field. So, therefore, we have the situation now is this: K to R, there is a natural inclusion, and R to the residue map R to R by M. This is a field and this is E1, and therefore I get an E1 and field extension of K. So K is here, let me call it E0. Then I have extended this to E1 and I will repeat this process. What process? I take all irreducible polynomials and adjoin and take the polynomial ring and consider the ideal and so on. So this is embedded in E2, etc., and keep doing this. This is embedded in EI, this is embedded in EI plus 1. So I have the chain of fields, and with what property? With the property that every irreducible polynomial EI in EIX has a 0 in EI plus 1. Every. See here, this is E1, and if you take an irreducible polynomial f here, we have that variable xf here, and this has a 0 here, namely the image of this xf, small xf. This xf is a 0 of f in E1. So that is what we are, that is how we have chosen this maximal ideal, which contain all these generators f of xf, and this goes to 0 here. Therefore, this property, and this we are doing it for every step. So, and now I want to say, we want to claim that I take the union now. E is the union of all these I bigger equal to 0, EI. This is the field, and we want to check that this is E is algebraically closed. And obviously each this stage is algebraic, and therefore E is algebraic over K. Okay. So how do you check? First of all, it's a field. Why? Because all these EIs are field, and therefore we can define addition and multiplication, and those will be well defined because it's a chain. So it becomes a field, and now I have to show that it's obviously algebraic over K, because each stage is algebraic over K and algebraic is transitive. Now we only have to justify that E is algebraically closed, but that means what? We want to check that. So to check that, to show that if I have a polynomial f in Ex irreducible, then I should prove that it has a 0 in E. But I know this f is one polynomial, so it will involve only finitely many coefficients. So therefore there exists an index I such that f actually has coefficients in EI. And if it is irreducible here, it will also be irreducible here. And therefore, by construction, f has a 0 in EI plus 1, but EI plus 1 is contained in E. So that's it. So this proves E is algebraically closed. So we have finished the proof of the Steinitz theorem, which says that every field has an algebraic closure. Now I want to remark here, which I don't know whether it will be proved in this course, but it is very, very important. The above process actually should stop at 1 only. So note that one can prove that already E1 is algebraically closed. This was remarked by Spicer, which if I have time I would comment it when we have the appropriate machinery. Okay. With this I will stop and continue in the next uniqueness of the algebraic closure. So, we will have to state it precisely and prove that it is unique up to a k isomorphism. This is what we will do it after the break. Thank you.